we've seen really three kind of types of circular motion problems, centripetal force problems to this point. The first one is the relatively simple one, relatively I say, where you've got maybe the speed of an object, the radius of the circle that the object is going in, maybe the mass of the object, and you're finding the centripetal force. There is one force that causes it. You don't know anything about that one force that causes it. All you know is, here's the speed, here's the radius of the path, here's the mass of the object, what's the centripetal force? That's it. The second kind of problem that we encountered is, hey, maybe there is only one force acting, but we know what that force is. Maybe it's a force of friction acting. Maybe it's a force of gravity acting. Okay, if that's the case, then we're going to set Fc equal to Ff, or Fc equal to Fg, or Fc equal to F, whatever it is that's causing it. There's only one force acting, and that force, whatever it is equal to the centripetal force. And finally, there's the last type of problem that we did where we have more than one force acting to cause it to go in a circle. And generally, that appears when we have a vertical circular motion problem. Okay, the vertical circular motion problem, we say F net is equal to the sum of the forces. That would be Fn plus Fg, right? Because always dealing with those same two forces, whether you're at the top or the bottom. And then we're going to say mv squared over r is equal to Fn plus Fg. So, don't be afraid to just use that equation. Okay, it's still valid, even though we haven't done a problem like that in a little while, other than maybe for your homework last night. Don't be afraid to use this. Fc is equal to Ff, or whatever other force that's causing it. But if there's more than one force acting, because maybe it's going in a circle or whatever, then let's make sure we do what we did in our last unit. F net is equal to the sum of the forces, which in this case, usually, would be Fn plus Fg. All right, that's all I want to talk about today before we check over our homework. We had a number of questions yesterday, questions 6 to 13. Any issues with any of those questions, Jeremy? Yep. Any others? 8, 12, and 13 it is. Number 8. Number 8, 1,500 kilogram car is making a turn with a 100-meter radius on a road with a coefficient of static friction is 0.7. What's the maximum speed that the car can go without skidding? This is the second type of problem that we were just talking about, right? We got one force acting. It is the force of friction. We can say Fc is equal to mv squared over r. That's perfectly fine. But we can also say Fc is equal to Ff. There's not more than one force acting. There's not gravity and a normal force, or friction and a normal force, or something like that. There's one force acting. So we're going to say either Fc is equal to mv squared over r, or Fc is equal to Ff. Now, odds are, because of what we're given in this question, we're going to say the second thing, Fc is equal to Ff. Let's give it a try. If something happens that doesn't work, then we'll try something else. Fc, the centripetal force, which is caused by friction, is equal to friction. So we say mv squared over r is equal to mu times the normal force. Now, the normal force, Jeremy, the normal force is what? Good. So we're going to replace Fn with m times g. And that's nice because it allows us to cancel out the mass. Now, even though we're given the mass, we are given the mass here, so we don't have to cancel it out. But it allows us to avoid plugging a couple more numbers into our calculator and lessens the chance of us making a mistake here. All right, so we got v squared over r is equal to mu times g. Let's rearrange this to solve for v. The r goes up by multiplying. So it becomes mu times g times r. And then to get rid of the squared, we got to square root that. So v is the square root of 0.70 times 9.81 times 100 meters. Do the math there, 26 meters per second. Now, final answer should be 2 digits as we've got there. This is 4, and this is that 3 or 2? What is it? That's 2 digits. The leading 0 doesn't count, right? So that's going to be 2 digits. Final answer should be 2 digits. Hey, what would happen if we didn't actually use this number? Okay, it's there, but we didn't use it. How many digits should the final answer be then? Yeah, we wouldn't count that for sig figs if we're not actually using the number. It's kind of like saying, you know, the 1,500 kilogram car is 2.2 meters long. And it's making a turn with this radius, whatever. If we're not using the length of the car, which we're clearly not in this question, then the 2 meters, the one significant figure there, is really irrelevant, right? All that matters is significant figures for what you're using. All right. Next question was number 12. Determine the centripetal acceleration on acting on a person standing at the equator. This one's interesting. We know the acceleration, centripetal acceleration, that is v squared over r, but we don't know what v is. We know what r is. That's good. We don't know what v is. So we got to find it, right? Uh, 2 times pi times the radius is given to me is 6.38 times 10 to the 6, divided by the period. How long? Oh, any ideas? So we got to find period somehow now, hey? The period of rotation of a person standing on the equator at the Earth. Peyton? Yeah, it's a day. It takes the Earth 24 hours to rotate on its axis, right, once. That's the period of the Earth's rotation. And if you're standing on the equator, that's the period of your rotation as well. So we're going to say it's 24 hours, but of course we want to convert that to seconds. 24 times 60 gives me minutes, times 60 again gives me seconds. And I think it's like 86,000 or something like that. 86,400. What does that give me for a speed? Surprisingly high. How fast is this guy moving as he's standing at the equator? Would you have predicted that a guy standing on the equator is moving at 1.5 times the speed of sound as he just stands there at the equator? It seems pretty fast. Okay? But in the end, he doesn't notice that because he's not speeding up. He's not slowing down. He's just going at roughly the same speed the whole time. So let's take that value now. Let's square it, 463.967, divided by the radius, which is 6.38 times 10 to the 6. And when we do the math there, what do we get? 0.034, and it should be 3 digits, right? 337, okay. 0.0337 meters per second squared, or we could say 3.37 times 10 to the minus 2 meters per second squared. All right. So here is how much centripetal acceleration is required to keep this guy on the ground, right? Keep this guy from flying off into space. That's the centripetal acceleration. How do we know that this guy won't fly off into space? Anybody ever think of that question? Like when you're younger, it's like, oh, if the Earth is spinning, and it's spinning really, really fast, and you've probably heard that before, that it is spinning really fast. Do you ever wonder why you're not flying off into space? Ethan, why aren't you flying off into space? Okay, gravity. What's the value of gravity? All right, so that's an acceleration, right? So the centripetal acceleration required to keep us on the Earth is 0.0337. What's gravity? 9.81. Is that enough to keep us on the Earth? And then some, by a lot, right? That makes sense, guys? All right, finally, number 13. It says an ant climbs onto the side of a bicycle tire at a distance of 0.40 meters from the hub. If the 0.010 gram ant can hold onto the tire with a force of this value, what's the frequency that the tire would have to move at to fling the ant off, assuming the wheel is spun in a horizontal plane? Hey, I'm picking up my red pen. How come? What do I want a red pen here? Yeah. Yeah, grams. I don't want grams. I want kilograms. So I'm going to convert that by dividing by 1,000. Okay, let's write down some givens here because there is quite a bit. We got something's 0.40. What's that? What does that correspond to? Yep, that's the radius, yeah. We got a mass here of 0.010 grams, or we could say 0.010 times 10 to the minus 3 kilograms, or you could just move the decimal place over 3 places. Even I get mixed up with that, so I just tack on a 10 to the minus 3 there. The force, all right, the force is 4.34. That's the magnitude of the centripetal force, 4.34 times 10 to the minus 4 newtons. And we want to find the frequency, hey? Ideas? What should we start off doing here? Go ahead. Okay, V is equal to 2 pi r over t. Good. Is that going to lead me somewhere? I don't know. I don't know if it's going to lead me somewhere. Is it a valid equation for an object moving in a circle? Yes. So don't ever be afraid to try something that's a valid equation. Okay. Bree says, I don't know if this is going to work or not. I don't care if it's going to work. Okay. I want you to try something that is valid. This is valid. Let's try it. If it doesn't work, okay, then the worst case scenario is I'm out 30 seconds of my life. Okay, I'll try something else. So what do we got here? We don't know what speed is. We do know what r is. We don't know what t is. So we get two unknowns there. Okay, right now, that doesn't seem particularly helpful. But we're going to keep it around because it's still valid, and it was a thought. It may become useful later on. Maybe it doesn't. Okay, worst case scenario is I used a little bit of ink. I used a little bit of time. Did get a wrong answer from it. Any other ideas? All right, go ahead. Yeah. Okay. Clearly, that's a valid equation if we're talking about an object moving in a circle. We know what FC is. We know what M is. We don't know what V is. We know what R is. So that allows me to solve for V. Okay, we're getting somewhere here. Okay, now when I see this, the fact that I'm able to solve for V, then all of a sudden I'm starting to think that that first equation that we wrote down might be useful as well, even though it didn't seem like it at the time. So let's get V there. Okay. Even as I do this, R goes up, M goes down, square root it to get V. Even as I do this, there is a small chance that even what I'm doing now isn't going to be helpful. Even though I'm going to solve for V, it might not work out for me. But it's not wrong. It's a valid thing to try, so we're going to do it. Times R is 0.40 divided by the mass is 0.010 times 10 to the minus 3 kilograms. Square root that. Who has a value for that? 4.16 meters per second. Okay. Thank you. Now that's the speed. What do you want to do with that, if anything? All right, so you're saying take this, rearrange it. T is equal to 2 pi r over V, 2 times pi times, what was the radius, 0.40, divided by V, 4.16. What's that give me? Do you have that, Nathan? No. 0.6023 seconds. That's still pretty close. Sorry, seconds? Yeah, that's right. Okay. We're not done, but clearly I think you can see that we're close to being done here, right? Colleen, what do you want to do now that we have the period and we want to find the frequency? T is equal to 1 over F. Good. We're going to rearrange that to solve for frequency. It's 1 over the period, 1 over 0.0623, and it's going to give me, I don't know, 1.5, 1.6, 1.655, which we should round to 2 digits, right? So you said 1.655? 1.7 then, right? Is that okay? How many people got that? Okay, good. This is the perfect example. I'm not trying to throw out hints for a test or anything like that, but this is a perfect example of that you got to know your stuff question, but not crazy trick question. Okay. I don't remember which questions are on the test right now. I haven't looked at this last unit test probably since it got made. Okay, and that's been a couple months. But listen, questions like this are great questions. Why? Because they require you to use pretty much everything you've done other than the vertical circular motion. Pretty much everything you've done in the unit here. But yet it's not like an elevator inclined plane slash pulley slash projectile motion question, right? It's a straightforward question if you know all of the stuff that we've done up until that point in the unit. Okay, so make sure you know that. Okay, focus on things like this because these are the types of things that we end up seeing on tests and on exams. Right? One more question to go over here. Number 10, NASA uses a centrifuge that spins astronauts in a capsule at the end of an 8.9 meter metallic arm. The centrifuge spins at 35 RPMs. Determine the, what's RPM mean, by the way? Rotations per minute or revolutions per minute. Determine the magnitude of the centripetal acceleration that the astronauts experience and how many times greater is this than the acceleration due to gravity. So how many G's is it, right? That's what they're asking in the second question. What do we got here? R is 8.9 meters. What's this? What's that? Victoria A, what's that? Good, it's frequency. Now, probably should have circled that in red because we don't want revolutions per minute. We want revolutions per second, which means we're going to divide this by 60. What does that give me? 0.55? 0.5833? Revolutions per second or hertz. What do we got here? We want to find the centripetal acceleration. That's it. That's all we got. All right, is what it is. Let's say, Nathan, what do you want to start with that? No, the other one. You asked the question, right, Nathan? You had asked that one? Yeah. Okay. 2 pi r over t. Honestly, I was expecting you to say something different. Okay, I was thinking something in the back of my mind. That's perfectly fine. Okay, I'm not even going to tell you what I was thinking because this is valid. Okay, if it doesn't lead us to something, then oh well, then we'll try something different. 2 pi r over t. We know what t2 is. We know what r is, I should say. It's 8.9 meters. But we don't know what t is. What do you want to do with that? Okay, so let's say over here, t is equal to 1 over f. 1 over 0.5833. And what'd you get for that? 1.8? 1.714? And that's going to give us a speed, which is, get that? 32.6? That doesn't seem that fast. Right? The astronauts are going at 32.6 meters per second. You go that fast in your car all the time. How can this be astronaut training? Well, you're going this fast in a car, but you're not going around a turn with a radius of 8.9 meters in your car. Okay, if you do that, then you're going to experience some G-forces, right? So we got something. Hey, it worked. We got something. It's not what we're looking for, but it's probably going to help me. What do you want to try next? Sure. 32.6 squared divided by 8.9 meters. What does that equal to? About 1,000 divided by 8.9. It's going to be, I don't know, 100-ish? 119.559. We're going to round that, actually, because we are looking for that number, so it is a final answer, 1.2 times 10 to the 2 meters per second squared. That's a big acceleration. Now, how do you find out how many times greater this is than the acceleration of gravity? How many G-forces is it? We're going to say 119.559 divided by 9.81. And that's going to give me about 12. 12. Okay, 12 G's. I'm not so sure about the accuracy of this question because astronauts don't generally don't train, I don't believe, at 12 Gs. 12 Gs would make you pass out. Even the best astronaut, even the most physically fit person would make you pass out probably well before you get to 12 Gs. That's why they do this kind of training, is to make you better at withstanding these G-forces. But no matter what the training, I don't think they're going to make you withstand 12 Gs for any more than a tiny fraction of a second. If you're a boxer and you get punched, you experience more than 12 Gs, but it's for a fraction of a second. If you experience it for several seconds, okay, you would pass out, okay, at 12 Gs easily. Okay. Most of us in this room would probably pass out before we reached 5 Gs, or at least just not very much more than that anyways. Got it? We're going to switch gears a little bit here now and talk about heavenly motion. What does that have to do with circular motion? Well, the fact that all of the planets revolve around the sun in almost circular paths, the fact that the Earth is orbited by the moon in almost a circular path, makes the motion of heavenly bodies, planets, moons, and so on, pretty relevant to what we've been doing, the whole idea of circular motion. The unit, if you remember at the beginning, is called circular motion and gravitation. We're going to start talking about gravity, and we're going to start putting gravity and circular motion together, just like we've already put friction and circular motion together, and normal force and circular motion together. We're going to give you a little bit of a history lesson first, though. We're going to go way back to before the birth of Christ, 2,000 years ago. Aristotle. Everybody's heard of Aristotle, right? 4 centuries before the birth of Christ. Ptolemy, 150 years, 140 years after the birth of Christ. Both put forth what we call the geocentric theory. Geo means earth, center means centered, or centric means centered. Geocentric, earth-centered theory. The earth is the center of the universe. We know that's not true, right? That seems so silly. The earth is the center of the universe. Everything else, including the sun, revolves around the earth. That's ridiculous. Is it ridiculous? If you woke up in the morning and you look up in the sky and you see the sun rising in the east, and then later on you see it down south of the school, and then later on you see it kind of southwest, and then later on in the evening you see it on the west side, what are you going to think? What are you going to think if nobody tells you differently? You're going to think that the sun is going around the earth. That seems completely logical to me. Just by anecdotal observations, it seems perfectly logical that the sun does go around the earth. We know it's not the case now, but we know it's not the case, at least most of us know it's not the case, because somebody told us, not because we looked up in the sky and said, oh, the earth is going around the sun. When we look up in the sky, it appears that the sun is going around the earth. So although it's wrong, it doesn't really seem so far-fetched. It seems like a completely reasonable hypothesis, given the technology that they would have had at the time. The sun and all the other planets and all the stars revolve around the earth in circles. Let's fast forward a lot of years here, like a couple thousand years, to Copernicus in the 16th century, the mid-16th century. You guys have all heard of Copernicus before, too. You might not know what he said, but he's pretty famous, actually, for this. Copernicus put forth the heliocentric theory. Helio means sun, sun-centered theory. All the planets, including the Earth, revolve around the sun. So it's not the sun revolving around the Earth, it's the Earth revolving around the sun. And all the other planets as well revolving around the sun. Heliocentric. Gets them into a little bit of trouble back then, because people for thousands of years had thought, hey, it's the sun that revolves around the earth. The earth is the center of the universe. People didn't want change. People didn't like change. But it wasn't long before there was some evidence to support this, as opposed to just anecdotal observations looking up at the sky. Let's go forward a little bit more, 50 years-ish. Tycho Brahe made naked eye observations of the planets with his assistant, Johann Kepler. What does that mean, naked eye observations? Oh, he looked up in the sky. He made some observations without the use of a telescope. He made observations with his assistant of times. How long does it take this star or this planet to go from this position to this position? Of angles. Okay, what angle is this particular planet at this time of day, at this particular time of year? Okay, how far does this travel and this planet travel, and so on and so on and so on. Made all kinds of naked eye observations of the planets with his assistant, Johann Kepler. Let's fast forward just a little bit longer to after Tycho Brahe dies. Hey, there's an interesting story about how Tycho Brahe died, by the way. So Johann Kepler, after Tycho Brahe dies, takes some of his data, crunches some numbers, says, you know what, we know the Earth revolves around the sun. We know the other planets revolve around the sun. But how do they revolve around the sun? What's their path? What does it look like? What are some of the laws that describe their motion? He came up with 3 laws using Tycho Brahe's data. Came up with 3 laws that describe the motion of the planets around the sun. So Johann Kepler comes up with 3 laws that describe the motion of these planets. The first law is called the law of the elliptical orbits. Now, this might seem odd because it looks like in the picture right now there's 2 suns. There isn't. And Johann Kepler never said there was 2 suns. Johann Kepler said that the Earth, or other planets for that matter, will go around the sun in an elliptical path. Not a circular path, but an elliptical path. Now, you can see the ellipse here. It's kind of an elongated circle. This is exaggerated. Kepler never said the ellipse was this much of a circle stretched. It's much closer to being circular than this. We draw it like this just so that you see, so that you can understand that it's not a circle. It is an ellipse. It's just real close to a circle, that's all. So the Earth, whenever I say the Earth here, I mean the Earth and all the other planets as well. They go around the sun in an elliptical path. Now, the sun isn't in 2 spots. The sun is in only 1 spot. But there's 2 focal points of the ellipse. 2 focal points. The sun is at one of those 2 focal points. So the sun is either right here, or the sun is right here. It's not at both. In fact, it doesn't move back and forth. And in fact, the sun doesn't decide where it's going to go because of where the Earth is going around it. It's the other way around. Rather, the sun is where it is, and then the Earth orbits around the sun, and other planets for that matter orbit around the sun as well, such that the sun is at that focal point of the ellipse, or the sun is at that focal point of the ellipse. So the Earth revolves around the sun in an elliptical path, and the sun will be at one of the 2 focal points. The sun is where it is, though. Remember, it's the Earth's path that is determined by where the sun is, as opposed to the position of the sun being determined by the Earth's path. Does that make some sense? Okay, I'll write this down in words here. We'll say the Earth, and once again, when I say the Earth, I mean the Earth and all the other planets, revolves around the sun in an elliptical path. With the sun at one of the 2 focal points. Okay, which came first, the chicken or the egg? Which came first, the sun or the Earth? Well, in this case, it's the sun, right? The sun is where it is. The Earth goes around it. All the other planets go around it, such that the sun will be at one of the focal points. That's more than we knew before, right? 2,000 years ago, we used to think that, or 2,500 years ago, we used to think that the Earth is the center of the universe and everything revolves around it. In fact, 1,000 years ago, we used to think that. It wasn't until the mid-16th century Copernicus comes along and says, no, wait, the Earth revolves around the sun. It's the heliocentric theory, not the geocentric theory. But even then, the Earth revolves around the sun in a circular path, presumably with the sun at the middle of that circle. Okay, fast forward a little bit, and all of a sudden, no, wait, it doesn't go in a circle at all. It goes in an ellipse, although it's much closer to a circle than what we see here. It goes in an ellipse. The sun is in one of two positions at one of the focal points of that ellipse. Second law, oh my goodness, this diagram looks even worse. Second law, called the law of equal areas. So we've decided where the sun is. It's right here. Let's color it in. There's the sun. The Earth is revolving around the sun in an elliptical path. The sun is at one of the two focal points. We'll make it the left focal point. Here's the Earth. Here's the Earth at position 1. Let's draw a line connecting the Earth to the sun. Now let's fast forward a little bit of time. Let's call it a month. Okay, 1 month later, the Earth is over here. Now it's at position 2. That line that joins the sun to the Earth has swept out a certain area. In other words, it's gone past a certain area, all this area right here. We're going to call that area A1. Now, don't ask me how to calculate that area. The area of the end of an ellipse, there's mathematics that would allow you to calculate that. I just don't know what that mathematics is. Okay, bottom line is, we could find it. Okay, if we knew enough about mathematics, we could find the area that this line joining the sun to the Earth swept out in a period of 1 month. Or, doesn't really matter what period of time we use. A day, a month, week and a half, whatever. There's an area swept out by the line joining the Earth to the sun in a certain amount of time. Let's fast forward 6 months. The Earth is over here now at position 3. There's still a line, an imaginary line that joins the sun to the Earth. In a certain amount of time, 1 month, we'll say, the Earth is over here. That line that joins the Earth to the sun sweeps out a certain area, A2, in a month, or whatever time we picked. Here's the thrust of this. A1 equals A2. A line joining the sun to the Earth, or any other planet, right, sweeps out equal areas in equal time intervals. If a month has gone by over here, and A1 has been calculated, and a month goes by over here and A2 has been calculated, then A1 will equal A2. Now, if 6 days have gone by, not a month, then area 1 won't be the same as what it was before. But if 6 days goes by over here and 6 days goes by over here, the areas are going to be different than they were, but they're going to be the same as each other. The area swept out by the line joining the Earth to the sun in equal time intervals is going to be the same. That has at least one really big implication. You can see here that if this time interval is the same, 1 month, as this time interval, clearly it travels more distance here in order to have the same area. What does that mean about the speed of the Earth? What kind of implication does that have for the speed of the Earth? Joseph? It speeds up and slows down. As the Earth approaches the sun, gets closer and closer to the sun and goes around it, it gets faster and faster and faster, and it starts slowing down. And then it starts speeding up again, speeding up, slowing down. And so on and so on. Now, the difference in speed of the Earth is not as dramatic as you might think by this diagram, because the ellipse isn't as dramatic as it is in this diagram. But, okay, this diagram makes the point that the distance covered in the same amount of time will be different, and therefore the speed will be different. Hey, and we know that's the case. We know that's the case. We've observed the Earth traveling at different speeds around the sun. We know when it's closer to the sun, it travels faster. Finally, the third law. We call it the law of periods. The law of periods is a more mathematical law, but we don't actually have to do the mathematics with it. we'll set it up, and we'll kind of leave it there. The law of periods says the square of the period of revolution of a planet around the sun. Now, for the Earth, that would be 365 days. Okay, the square of the period of revolution, 1 year for that planet, is proportional to or is related to the cube of the average radius of revolution. Now that changes, right? The radius of revolution changes depending upon where it is in its orbit around the sun. R is the average radius of revolution. These two numbers are related to each other. In other words, as R cubed goes up, T squared goes up. What does that mean? Well, if you've learned anything about proportionalities in math class, it means that T squared is equal to something. Just a number. We call it a constant times R cubed. So T squared might be equal to 1 times R cubed, or it might be equal to 3 times R cubed, or it might be equal to 6.5 R cubed, or it might be equal to 6.67 times 10 to the minus 11 R cubed. But K would always be the same. No matter what T is, no matter what R is, the value of K would be the same. Let's rearrange this a little bit. K is equal to T squared over R cubed. What this means is this. There is a constant called Kepler's constant. And that value is not universal across the universe, but that value is the same for every object as it's being orbited. So in other words, if you've got the Earth revolving around the sun, if you've got Jupiter revolving around the sun, if you've got Saturn revolving around the sun, and Mars revolving around the sun, then the value of K for the sun will be the same no matter which data we use, the data for which planet that we use. For instance, Kepler's constant for the sun could be equal to T squared over R cubed for the Earth, but it could be equal to T squared over R cubed for Jupiter, or it could be equal to T squared over R cubed for Mars. Every object revolving around the sun, using data from that object, will produce the same value of K, Kepler's constant for the sun. Now, similarly, Kepler's constant for the Earth might be T squared over R cubed for the moon. Or Kepler's constant for the Earth could be T squared over R cubed for a space station or some satellite orbiting around the Earth. These two constants are the same. These two are the same. But these two are not the same. So what? How is that useful to us? Seriously. Here's the deal. If we know data about the Earth, let's say, T squared, T and R for the Earth, we can get a value for Kepler's constant. From that, we can determine information about Jupiter. So we can actually use information about one planet to get information about another planet. That's why it's useful. It's easier to measure the time that it takes the Earth to go around the sun, the distance from the Earth to the sun, than it is to measure something about Saturn. So let's use data from the Earth's revolution around the sun to find data about Jupiter's or Saturn's or Neptune's or whatever planets orbit around the sun. Does that make sense?